Hi, welcome back to CS560. So from this lecture on, we are going to talk about graph algorithms. And this is the part one of it, and we'll basically cover the elementary graph algorithms. So graph is a very important data structure in computer science, and it's really pervasively used. And for example, if you want to represent a circuit network or internet, social networks, and nowadays in artificial intelligence applications, we can represent a dictionary of millions of words or a knowledge graph with graph data structures. So graph problems are really a pervasive problems in uh, multiple areas of computer science. Okay, so in this lecture, we are going to cover how we represent a graph in computer with different types of data structures. Like we'll notice, we will introduce concepts like vertices, edges, and weights, and so on. Okay, and more importantly, we will start with some basic searching algorithms that help us go through each vertex in the graph or each node in the graph. So these types of algorithms like breadth first search BFS or depth first search DFS, they belong to the general problem of how to efficiently search a graph. And also, in our next video lecture, we'll talk about more advanced algorithms, more advanced problems like how to obtain the spanning tree that has the minimum weights within the graph. Okay, and these these problems are meaningful when you want to optimize something or more optimize the properties with respect to a graph. Okay. And lastly, we'll also talk about the classical shortest path problems that basically help you find, given a graph, how do you determine the shortest path between any two or multiple vertices. Okay, so in this lecture, we'll start with the representation, different ways of representing graphs in computer. And then we'll talk about two algorithms, the BFS, breadth first search, and the depth first search of a graph. Okay. So we will first introduce several notations when we represent a graph. So we use a capital letter G to indicate a graph, and a graph consists of a set of vertices. Okay, and we use the capital letter V to indicate the set of all the vertices. Okay, and also the capital E to indicate the set of edges. Okay, so one edge connects a pair of vertices. That is to say, two vertices at the two ends of one graph of one edge. Okay, so altogether we can say that G is parenthesis V and E. So we can use this compact way to represent the graph G, saying that G has that many, all the vertices in G are contained in V, and all the edges are contained in capital E. Okay? For example, this is a very simple graph that has 5 vertices from 1, 2, 3, 4, 5. Okay, so all the circles with gray background, and the numbers in it, they indicate all the vertices. Okay? And all the lines that connect those vertices are the edges in this graph. Okay? So here we say the set of vertices capital V is a set of from 1, 2, 3, 4, 5, a set of integer numbers. Okay? And we use lowercase letter to indicate one edge. So the set of edges is A, B, C, D, E, F, G. Okay? So this is a very simple example of how a graph may look like. So you may have already noticed that not all the two vertices are necessarily connected to each other. Like in this case, 1 and 4, the vertex 1 and 4, they are not directly connected. There's no direct edge between 1 and 4. Okay? Or 1 and 5, right? So we'll use the notation of the size of a set to indicate the number of vertices or number of edges. Okay, so we put the capital V between these two vertical bars. Okay, so this indicates the number of vertices, and E between these vertical bars are the number of edges. So in this particular case, we have 5 vertices. So the size of V is 5, and we have 1, 2, 3, 4, 5, 6, 7 edges. So the size of E is 7. Okay? So it's always satisfied that the number of edges should be smaller than or equal to V times V, or the size of V raised to the power of 2. So this is if you think of it, so if you think about it in this way, like if you take any two vertices from the graph and they are connected, there's an edge in it, then the total number of vertices is V times V. So including the case where the vertex is connecting to itself, right? So because when you define an edge, you need to choose one end first and then choose the second end, right? So when you have V possible choices for the first end and also V possible choices for the second end, then the total number of combinations is V times V. Okay, so that is the maximum number of possible edges. So that's why E is always bounded by this quantity. Okay, so we can also we also have two types graphs when we look at the edges. Okay, the edges could be directed or undirected. So as the name indicates, a directed graph, we have all the edges coming with arrows. Okay, so in this graph, the edge between 1 or 2 is directional. It connects from 1 to 2, not the other way around. Okay, and there between the vertex 2 and 4, there are two edges. Okay, because we treat them differently. In a directed graph, we view that the edge from 2 to 4, which is pointing downwards, is a different edge from the one beside it, from the edge pointing from 4 to 2. Okay? And the second type of graph is undirected graph. And basically, all the edges in it are just plain lines without arrows. Okay? And also, there's a special type of graph that have weights on each associated with each edge. Okay, so we define this graph as weighted. We call this graph as weighted graphics. So in the weighted graph, each edge has a number or has a weight associated with it, and it's typically a real number, and it's given by a weight function that map each edge in E to a real number. Okay, so the weights in this example are indicated by the numbers above the edges. So the edge between vertex 1 and 2, it has a weight of 7. Okay, so this is a very practical setup, because when we use a graph to represent a real world problem, the edges could, in this case, it can indicate the distance between, say, cities or airports, right? Or the distance between two different semantic concepts, like the words are very different from each other or very unrelated to each other. They may have very small weights along the edges. Okay, so this one place that you may want to notice is that this weight, it could be a real number, or it could be negative, it could be 0. Okay, it doesn't necessarily need to be an integer numbers. Okay, so these numbers like 7, 8, 11, 9, 4, 7, 6, they are not the indices. They are not integer indices. They could be any numbers. Okay, so now using the given notations, we can represent a graph, or we can implement a graph in computer with 2 ways. Okay, so with a graph mathematically defined by a set of vertex V and a set of edges E, we can use 2 ways to implement it in computer. The first way is a collection of adjacency lists. So we call this is our first method, adjacency lists. So note that here the lists is a plural form, so there are more than one list. Okay, so it's a couple of lists. And the second way is adjacency matrix. Okay, and these 2 ways, they have pros and cons, and they are suitable for different graphs. And usually speaking, the adjacency lists is more commonly used for sparse graph, in which there are much fewer edges than the number of vertices. Okay, and the adjacency matrix are more commonly used if it's a dense graph. That means there are a lot more edges, and it's so in this course, I think most of the algorithms that we implement later on will utilize the adjacency lists method to represent the graph. Okay, but both methods, they are worthwhile to look at, because they all provide very efficient ways to implement graphs data structure within the language of computer science. Okay, so the first method, adjacency lists, to implement a graph, we need to use a data structure called list or linked list. So it is similar to array, but it has a pointer part in each element. The end of the element is a pointer that points to the next element. Okay, so with this method, within a graph of g equals v of e, it consists of an array named Adj, which is for adjacency. Okay, so this is an array, and it has that many lists, the size of v lists, and each one of these lists is for a vertex in v. Because in V, we have that many vertices, and for each vertex, we give it a list. We assign it a list. That's why we have size of V, that many lists in total. So what do we do with this list? For each vertex in V, for each vertex U in V, and its adjacency list is Adj of U, because Adj is an array, and the U element in Adj is the list that associated with the vertex U. And within this list, it contains all the vertices V such that there is an edge from U to V within the set of all edges. Okay, so here the U comma V within the parentheses U and V, it represents a edge from vertex U to vertex V. Okay, so basically speaking, the list Adj of U contains all the neighboring lists, contains all the neighbor vertices of U, and there is a connection, there is a direct edge from U to V. Okay, or we call this all the vertices in Adju consist of all the adjacent vertices to U within the graph. So within this example here, if the graph is undirected and the Adj property of G looks like this, because we have 5 vertices, and that's why we will have 5 lists as well, and each list is in a row. Okay, so within the first row, it is the list for vertex 1. So it starts with the vertex 1 and it connects to vertex 2. Okay, because 2 is adjacent to 1. There's an edge from 1 to 2. And the 2 will connect to 5. Oh, no, the 2 will connect to 5 because the vertex 5 is also a vertex, adjacent vertex of vertex 1. Okay, so this first row, the first list from 1 to 2 to 5, it consists of all the adjacent vertices for vertex 1. So if you look at the second row, it contains all the adjacent vertices to vertex 2. So that's why there are 1 and 5 and 3 and 4. Okay, so actually within this particular example, the order of these vertices within each list is not important. It could be a different order because we didn't give any rules in deciding how we need to arrange the orders. So as long as all the adjacent vertices they appear in the list, then we say this adjacency list is a complete representation for this graph. Okay, and the second example, if we use a directed graph as an example, in this case it's a bit different, because if you look at the first row, it is all the adjacency all the adjacent vertices of vertex 1. It should be 2 and 4, right? This is no problem. Okay, but for 2, for all the adjacent vertices of 2, there's only one vertex, which is 5, because the edge from 2 to 5 exists in the directed graph, but there's no edge from 2 to 1. Okay, and also there's no edge from 2 to 4. That's why 1 and 4, they don't appear in the second list. Okay, they don't count as the adjacent vertices of 2, but they do appear. So 2 do appear in the adjacent vertex of 1 in row 1, and 2 also appear within the adjacent vertex of 4 within the 4th row here. Okay, so this is a very interesting difference between directed versus undirected graph. And also another interesting place is the vertex 6. It has a loop that connects back to itself. So the 6 is an adjacent vertex of itself. So that is the adjacency lists representations of a graph. And this kind of adjacency list representation has some interesting properties. Okay, so we can use the number of, or the size of adjacent lists to decide to relate it with the number of total graphs, or number of total edges within the graph. So if the graph is directed, then we say the sum of lengths of all the adjacency lists is the size of capital E, which is the number of edges in total. Okay, so for example, here it is the directed graph that we just showed in the previous slide, right? So if you count the number of edges, so let's count the number of the sizes, the length of each vertex, each adjacency list. So the size of the first adjacency list is 2, right? It has 2 adjacency numbers. And the second adjacency list, it has just one element, right, which is 1, and the size of the third one is 2. So all these numbers, they add up to 8, okay, which is exactly the number of total edges. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so but it's a different property if the graph is undirected. Okay, so in this case, if it's an undirected graph, then the sum of all the lengths of all the adjacency lists is 2 times the total size of edges. Okay, so using the same example from the previous slides, if we count the lengths for each adjacency list, then the length for the first one is 2, and the length for the second one is 4, and then 2, 3, 3, and they all add up to 14, which is 2 times the total number of edges, right? 1, 2, 3, 4, 5, 6, 7. Okay, so this is because the edges, they are counted twice, or all the adjacency lists, adjacency vertices, they are counted twice. Okay, so when we count the number, when we find the adjacency vertices for vertex 1 here, we count 2 and 5 as adjacency vertex for 1, right? So that's why they appear here. But later on, when we count the adjacency vertices of 2, we count 1 again here, right? So that's why the edge from 1 to 2 and from 2 to 1, it is counted twice. That's why for the case of undirected graph, the total number of adjacency lists should be 2 times the total number of edges. Okay, but this is not the case for a directed graph, because in a directed graph, if there's no, so for these edges that's pointed in, we don't count it as an edge. Okay, so that's it for the adjacency list representation. For the second method, adjacency matrix, we will need to use a V by V matrix. Okay, and so that within this matrix, the elements at the ith row and the jth column is 1 if the edge from vertex I to vertex j exists in the set of edges. Otherwise, this element is 0. Okay, so take this example. If it is an undirected graph, then it has 5 columns and 5 rows. Okay, and if you look at the first row, the elements 1, 2 is 1. That means the edge that connects from vertex 1 to edge to vertex 2 exists in the graph. So that's why there is a 1 here. And also because the edge 1 to 5 also exists, so that's why the elements at the first row and the fifth column, A1, 5, is 1 here. Okay? And this is an undirected graph. So interestingly, this whole matrix, it's a symmetric matrix along the diagonal direction of this matrix. So if you transpose the matrix, it remains the same. Okay, so for example, the elements A12 is 1, and that's why A21 is also 1, and A23 is 1, and A32 is also 1. Okay, because when you consider adjacent vertices, all the edges, they are counted twice. And if it's a directed graph, then the matrix look like this. Okay, so from 1 to 2 exists, so there's a 1 here, and from 1 to 4 also exists, there's a 1 here, and from 2 to 5 exists, so there's a 1 here, and 6 to 6 exists, so there's a 1 here. Okay, so this is a second method of adjacency of how to represent a graph in computer. So as you see in this example, there's a lot of zeros. Okay, because there are not so many edges as compared to the number of vertices. So there are fewer ones than the number of zeros. So that's why this adjacency matrix is not a suitable choice when the graph is very sparse. Okay, so that will result in a lot of unused elements in this matrix. Okay, so and also you we will find that the adjacency list is a more flexible way to represent a graph, because it's easy to program and easy to implement. Okay, but in nature, these two methods, they are interchangeable. Okay, so if it's a sparse graph, if you prefer, if you still want to use a matrix to represent it, you can use techniques like sparse matrix implementation to avoid storing a whole lot of zeros in your memory. Okay? And so this is the representing techniques to represent a graph in computer. And next we're gonna talk about how we search a graph, and basically we focus on two methods: breadth first search and depth first search. Okay, so searching a graph basically means that we want to systematically follow the edges so that we can visit all the vertices within the graph. Okay, we want to follow some rules in order to go through all the vertices and following all the edges. Okay, so by searching the graph, we can obtain information that are useful to understand the graph's structure. So it is basically the heart of a lot of other graph algorithms. Okay, so we'll talk about breadth first and depth first. So the first one is depth first, BFS, and so the problem is like, given a graph G of V and E and some source vertex S. Okay, so this S is where we start our search. So it is the starting point. Okay, so BFS will explore the edges of G to discover every vertex that is reachable from S. Okay, so this BFS algorithm will compute the distance defined. So this distance is defined by the smallest number of edges from the starting vertex S to each reachable vertex, and it will produce something, some tree structure like that use the roots, that use the source vertex S as its roots, and it's called the breadth first tree as a result of the breadth first search. Okay, so after the BFS is done, any vertex V that is reachable from S, we can have a simple pass in the tree, in the resulting BFS tree, from the root S down to the vertex V, and these paths correspond to a shortest path within the graph that connects the vertex S and the vertex V. Okay, so we're basically kind of converting the graph to a tree, and each node within the tree has a number computed, and that number basically tells us how far away that vertex is away from the root node or root vertex S. Okay, so the breadth first name comes from the fact that this BFS algorithm will discover all the vertices at a smaller distance first. So we'll discover all the vertices within distance k first, before discovering any vertices that are outside the current distance. So any vertices that are k plus 1 away from S will be discovered after all the nearer vertices within distance k are discovered first. So that's why it's called the breadth first search. Okay, so within this, when we implement this BFS algorithm, we need to define three types of vertices here. We need to have white vertex, gray vertex, and black vertices. Okay, and BFS will color each vertex into three colors. So all the vertices, they are initially white. So before we visit them, they are white. Okay, and a vertex will become non-white, either gray or black, the first time it is discovered. Okay, as long as it is discovered, then it is not white anymore. Okay, and So that means the grays and the blacks, the gray and black vertices, they are already discovered. Okay, so the gray vertices may have, and difference between the gray and the black vertices is that the gray ones may have adjacent to white vertices. Okay, and all the adjacent vertices to black vertices, they are all discovered. So that is a major difference. So the gray ones, they may reach to undiscovered vertices, but all the neighboring vertices to black ones, they are already discovered. Okay, so so basically speaking, the grays, they represent the frontier between the discovered and undiscovered vertices. So the undiscovered ones, they are whites, and the gray ones are lies in between. It connects the discovered vertices and the undiscovered vertices. Okay. So as we just said, the BFS will construct a breadth first tree. It will eventually construct some tree-like data structure. And within that tree, the root is the source vertex S. It is where we start. Okay, and we assume that the vertex U is already discovered. Then we can scan its adjacency list by accessing G, which is the graph, .adj, which is the lists, which is the adjacency lists, and we use the index U to access the corresponding list that contains all the adjacent vertices of U. Okay, so whenever a white vertex is discovered, we will add that vertex and the edge from U to V to the tree. Okay, and we say that U is the predecessor or parents or ancestor of V. Okay, so we usually say parents because it's a direct predecessor of V. Okay. So, and each vertex is discovered at most once. So it has at most one parent. Okay. So these are just some technical details that we're gonna use later on when we implement the pseudocode. And this slide, I think it's more serves as a providing you a bunch of notations that will be needed. So we will talk about trees, we'll talk about the parents of node within the tree, and also we'll use the adjacency list representation of a graph. Okay, so from next slide on, we will see how we implement the BFS algorithm with pseudocode. So here is the pseudocode for the BFS procedure. Okay, so this segment of code, it's a procedure that takes into the graph G and a starting vertex S as inputs. So assume that we represent the graph with adjacency lists. Okay, and also we assume that each vertex in the graph has an attribute called color. Okay, indicates whether it's white or gray or black, and also it has a second attribute D to record its distance from the source. Okay, and the third attribute pi to record its parent node within the BFS tree. Okay, so the main body of the procedure consists of a for loop at the beginning and the while loop at the end. Okay, and within the while loop, there's also another for loop. Okay, So the function of this first for loop is simply to initialize everything. Okay, so it iterates over all the vertices except for the starting vertex, because we're already there. So it paints all the vertex within this for loop to white color and the distance to infinity and their parent node to none. Okay, because all the other vertices, they are not visited yet, and the white color indicates unvisited or undiscovered vertices, and the distance is unknown, so that's why it's set to infinity, and all the parents relationship are also unknown, so that's why this pi property, this pi attribute is also none. Okay, and from what comes next from line 5 to line 7 is also a initialization that paints the color of the starting vertex S to gray, because this is where we start and it's first discovered, so that's why it's painted to gray, and the distance is 0 because this is where we start, so the distance is 0. Okay, and the parent is also 0 because there's no other vertices that are above S in the resulting BFS tree. Okay, so there's no parent of S. Okay, so from line 7, quite straightforward initialization, and from line 8 on, from everything below line 8, they are kind of serves as the function of visiting all the possible vertices in the graph. Okay, so line 8 and line 9, we initialize some data structure. We'll initialize a queue data structure. Okay, so a queue, which we already used a lot before, it's a first in and first out data structure. Okay, we can in-queue an element into the queue, and then we can dequeue the elements at the head of the queue. Okay, so everything in-queued appended to the tail of the queue, and everything that got dequeued is from the head of the queue. Okay, and this queue is important in this procedure because it helps us to manage all the gray vertices. Okay, we need to use this queue data structure to hold all the gray vertices. Okay, as you will see how it goes, how things works around. Okay, so first we will need to in-queue the starting vertex into the queue. Okay, to make that queue non-empty, so that the while loop will get executed. Okay, so this while loop will keep running as long as it's not empty. Okay, so as long as there remain gray vertices. Okay, and the first line of the code is to dequeue. That is to say, we remove the gray vertex at the head of the queue. Okay, we take the first elements from the queue out, and we call it vertex U. Okay, and then within the inside for loop, we use a for loop to go through each vertex within the adjacency list of U. Okay, U is the vertex we just dequeued, and we visit all the adjacent vertices of U by using this g.adj with index U. Okay, for each V vertex in it, we will visit it. So, and from line 13, we check whether that adjacent vertex V is white. Okay, if it is white, then it means it is not discovered yet. Okay, So we will paint it to gray, okay, and to mark that vertex V as discovered by painting it gray. And then we will set its distance, set the distance of V to the distance of U plus 1. Okay? And the parents of V to be U. Okay? Because V is adjacent vertex of U, and we discovered U first. Okay, so all of it's discovered, all of U's adjacent vertices that are discovered later, it should have longer distance from the source. Okay, so that's why the distance of V is the distance of U plus 1, and U is the parents of V. Okay? And after that is all set, we will need to enqueue that just discovered V into the queue, back to the queue. Okay? Because V is now gray, and we need to enqueue it to DQ, to the queue. Okay? So what's after line 7 is line 18, which paints U to the black color. Okay, because after the for loop from line 12 to line 17 are executed, all the adjacent vertices of U, they are all discovered. Okay, and that means there's no undiscovered adjacent vertices of U. Okay, so U doesn't need to be gray anymore. It can be marked as black. Okay, which means the neighbors of U, they are all visited. So U is no longer at the frontier between the discovered and undiscovered vertices. Okay, so that's it for all the code in BFS procedure. So there's a something about the loop invariance of this while loop. So it says the queue consists of the set of gray vertices. Okay, so every vertices within the queue must be gray. There shouldn't be white or black vertices at all. Okay, this is true because every vertex is first painted gray at line 14, right? And then enqueued. Okay, so that relationship guarantees that every vertex that is enqueued is first painted gray. Okay, and whenever a vertex is dequeued, it will be painted black. Okay, so these two statements basically proves that the loop invariance is true. Okay, everything within Q is gray vertices. So that's the walkthrough of this procedure, and from next slide we'll use a simple example to see how the BFS works on a simple graph. Let's look at this simple example of running BFS on the graph. Okay, so assume that the graph looks like this. It's an unidirectional graph, and the vertex S is where we start. Okay, so if we just look at the initialization part of the code first, so we will use a for loop to paint all the other vertices except the source vertex to white. Okay, everything are white, and all the distance are to infinity, and all their parents property attribute is also none. And for the source vertex S, its color is gray, okay, and its distance is set to 0, okay, and its parent is also none, okay. And then we we initialize the Q, and then we enqueue S to Q, okay. So now S is within the Q here. So the next step, we'll look at the while loop. Okay, the while loop will first dequeue the head elements, right, and go through the all the adjacent vertices of that vertex U, use another for loop inside, and then if that vertex is white, then we will paint it gray, increment its distance, and assign a new parent to it, and then enqueue that adjacent vertex back, and finally we'll paint that U to black. So let's see what it looks like when we run it on this example. So the dequeue will remove S from the Q, right? And for each adjacent vertex of S, from the graph we see that W and R, they are the two adjacent vertices of S. Okay, so the code of the for loop will go through W and R and paint them gray, right, and increment their distance by 1, or exactly speaking, it's not increment, it's assign their distance to the distance of their parent node plus 1. Okay, because the distance of S is 0, so that's why their adjacent vertices W and R, the distance will become 0 plus 1, which is 1. Okay, and then W and R are enqueued to the Q. Okay, and then finally the color of S will be painted to black. Okay, because all of its adjacent vertices are visited. Okay, so this is just the first iteration of the while loop, and next, starting from the next the next iteration of the while loop, the new head at the Q will be dequeued. Okay, so the new head is W, so W will be dequeued within the next iteration, and all the adjacent vertices will be visited. All the adjacents of W will be visited. Okay, so the adjacent vertex of W include S and T and X, but since S is already black, it's no longer white, so we'll skip S and then we'll go to T. T was white, so it's painted to gray, and the distance is 1 plus 1, which is 2, and it's enqueued back, okay, and which follows the R, and another adjacent vertex of W, X, is also painted to gray, and the distance is 1 plus 1, and it's enqueued back to the Q, and afterwards the W will be painted to black as well. Okay, so now we have 3 elements, R, T, and X. Okay, so you see we also show the distance properties for each vertex here, 1 and 2 and 2. Okay, so the head vertex always have smaller or equal always has a minimal distance within the Q. Okay, so the next iteration we will dequeue R from the Q. Okay, when R is dequeued, its adjacent vertex S and V are visited. Since S is black, only V will be painted to gray, and the distance will be plus 1 plus 1, and the V will also be enqueued. Okay, so now the Q, they contain gray vertices of distance 2. Okay, so the next vertex got DQ'd is T, right? When T is visited, when T is DQ'd, its adjacent vertex U and X are visited, and U is painted to gray and inQ'd back, and next X is DQ'd and Y is inQ'd, okay? And finally, when there is V and U and Y in it, V is DQ'd and it got immediately painted back black because there's no undiscovered adjacent vertex of V. And after U is DQ'd, it's instantly painted black. And Y also instantly painted black. Okay? So eventually when the Q is empty, the whole elements, all the vertices within the graph is visited. So that's how the BFS algorithm runs under a very simple example here. I hope you can run this on the paper yourself so that the whole DQ and InQ processes got really clear to you. Okay, so now let's analyze the running time of BFS procedure a little bit. So looking at the code, because each vertex is inQ'd at most once. Okay, when it's gray, it's inQ'd. And it's also DQ'd at most once. So, and each Q operation takes constant time. Let's say inQ and DQ is quite fast. So the total time for Q operations is big O of V, because there are many vertices in the graph. And so the key point is the nested for loop, nested loops with a while at the outside and the for loop in the inside, right? So because the for loop starting at the line 12, it's basically go through the adjacency list of each vertex only when it is DQ'd. Okay, so that means only when a vertex is DQ'd, it is scanned. Its adjacency list is scanned. So each adjacency list is scanned only once. Okay, so now recall that if it's an undirected graph, since the sum of the lengths of all adjacency lists is two times E, and for a directed graph, it's just E. So the total time of scanning all the elements in all the adjacency lists is big O of E. Okay, it's a linear time with respect to E. Okay, so putting that together, the total running time of the BFS should be the big O of V plus E. Okay, so it is determined by the size of the graph, which is in which you need to consider two quantities, both V and E, both the number of vertices and number of edges. So next, let's look at the results of the breadth-first tree of the BFS search. So as we said, it is something like a tree structure. Okay, so looking at these results from running the example from the previous slides, it is something like this. All the vertices, they are painted black, and there's a number within the vertex indicating the distance from that vertex to the source vertex S. And also there's a parent's attributes assigned to each vertex. Okay, so with these results, now you can imagine that you put your hand upon the vertex S and you lift the whole graph up, and all the other vertices, they will naturally flow down. So you will got a tree structure like this, and all the vertices with the same distance attributes, they will hang at the same level. Okay, R and W vertices, their distance is 1. Okay, so they are at the level 1, and t, x, and v, their distance is 2, so they are at the level 2, and the u and y, their distance is 3, so they are at the level 3. So that's how we can obtain a tree structure from the results of running BFS. And more importantly, from the tree, we can find a corresponding relationship by observing a simple path from the root node S to each vertex. Okay? For example, if we draw the path from the S to Y, this is a shortest path in the corresponding graph. The path from the root node S to Y in the tree is the shortest path from the vertex S to the Y vertex in the graph. Okay, so this shortest path is defined by the number of edges between S and Y. Okay, so this path basically has the minimum number of edges between S and Y. So if you go through the other paths from S to W to T to U to Y, then it is longer than this path, because in this path there's only 3 edges. Okay. So a little bit more about the concept of shortest path. BFS can find the distance to each reachable vertex in the graph from a given source S vertex. So we can define the shortest path distance between 2 vertices, say S and V, the delta of S and V, as the minimum number of edges in any path from vertex S to vertex V. Okay, so it is defined by the number of edges, and any path that has the minimum number of edges, we call it a shortest path. Okay, so if there's no shortest path from S to V, that means it is not reachable. V is not reachable from S, and that's why the shortest path distance delta is infinity. Okay, and a path of length, any path of that length is a shortest path from S to V. So there could be more than one shortest path from S to V. Okay, so we can use this definition to kind of prove that BFS is correct. So it's called the correctness of BFS theorem. So this theorem says that when the BFS is done, then the D attribute for each vertex is the shortest path distance from the source vertex to V for all the vertices in the graph. So that's what this theorem says. So I will say it again. So this theorem basically says that the D property, after BFS is done, the D attributes, it records the shortest path from S to that vertex. Okay, and this is a very important property, because when the BFS is done, you can directly read the D properties from each node to know how far away that vertex is from the source vertex. Okay? And one of the shortest paths from S to V is a shortest path from S to the parent of V, followed by the edge that connects from the parent of V to V. Okay, so it is an incremental relationship. So once you know the parent of V, you can basically get the shortest path by appending the segments from the parent of V to V to the parent of V, so that you get the shortest path from S to V. Okay, so it may be a bit lengthy in language, but it's a quite straightforward relationship. Okay, so how to prove this theorem is not required in the class, in our course, but it's interesting if you read them from the textbook. Okay, so now using the parents relationship that we assigned to each node when we do the BFS search, then we can use this relationship to use this information to print the shortest path given any vertex within the graph. Okay, so assume that we have already run BFS once on G, and we can use this procedure to print the path from S to V. Okay, so it is a recursive algorithm, and basically, if it's the source vertex, and it will just print itself. If there's no vertex, there's no parent vertex of the current vertex, then we say that there's no path from S to V. Okay. Otherwise, we will recursively call the algorithm on the S, which is not changed, and the parent of V. Okay, and then we will print V. Okay. So, looking at this result of running BFS, if you think of it, how print paths on S and Y work. Okay, so the call on S and Y will result the call at line 5, right? Call on S and the parent of Y, which is X. Okay, and the call of S and X will result in another call on S and W, okay, and on S and S. Okay, the call on S and S will just print S, and then W will be printed, and then X will be printed, and then Y will be printed. So that's how this recursive call will print all the vertices along the way from the shortest path, along the way of the shortest path from S to Y. Okay. And that's it. Everything about the BFS implementation. If it's the first time you read about this algorithm, I think it really helps out if you can run with the example on a paper, and to especially pay attention to when the vertex gets dequeued, and how the adjacent vertices of that dequeued vertex is scanned, and then how all the scanned vertices are enqueued back to the queue again. Okay, and the difference between the three colors, gray and white and gray and black, they are also critical informations how to separate the discovered and undiscovered vertices. And that's it for the first graph search algorithm, BFS. And in the next lecture, we'll talk about the depth first search.